All right, folks, welcome back to AI Paper Podcast. Today, we're diving into a paper that's got people talking in the machine learning world.
It's a good one.
Yeah, it asks this kind of crazy question. Can transformers, those powerful language models, actually predict pseudo-random numbers?
And the answer is, drum roll, please, yes.
That's wild. So how do they even approach this? What kind of setup are we talking about?
So they focused on the specific type of pseudo-random number generator.
Okay.
It's called a linear congruential generator, LCG for short.
LCG, got it.
And you can kind of think of it like a recipe for making numbers that look random. But under the hood, they actually follow a pattern.
Like a hidden pattern.
Exactly.
Interesting.
And the pattern depends on a few key ingredients. Like, when you bake cookies, you've got your flour, your sugar, your butter.
I see where you're going with this.
Right. So with LCGs, these key ingredients are the modulus, the multiplier, and the increment.
Okay, so they're not really random. They're just following a formula.
Right. It's deterministic.
Deterministic.
So the researchers, they trained these GPT-style transformers on sequences generated by these LCGs. And what they found, it's pretty amazing, is these models could actually crack the code.
So they're figuring out the recipe, essentially.
Yeah, they're predicting the sequence of numbers even when, the parameters, those ingredients we talked about, are changed up.
So they're, throwing different ingredients at it, and it's still figuring it out?
Exactly.
That's impressive.
And it gets even more impressive.
Oh.
They actually explored two scenarios. One where the modulus, that's kind of the main ingredient in the LCG recipe, stayed the same during training and testing.
Okay.
But then they had this other scenario where the model had to predict sequences with moduli it had never seen before.
Whoa. So it's like, okay, you've learned to bake chocolate chip cookies.
Right.
Now, figure out oatmeal raisin without ever having seen the recipe.
Exactly. Can you taste this cookie and tell me not only the recipe, but what the next batch will taste like, even if I change the flour?
Okay, my mind is officially blown. This is just in the first few minutes, so before we go any deeper.
Sure.
Can you give us, a TLDR, the key takeaways of the paper so our viewers can get the gist right up front?
Yeah, absolutely. So in a nutshell, this paper shows that transformers, they have this remarkable ability to learn and to exploit hidden algorithms within data that seems random.
Okay.
And the way they do it is they break down the numbers into this thing called their residual number system representations.
We'll have to unpack that, I think.
We will. And they use some clever tricks with context to make the prediction tasks simpler.
Interesting.
And what's really cool, the researchers, they found specific components within the model itself.
Oh, so they're really peering into the black box.
Yeah. And these components, they seem to be responsible for different steps in the process, like which part is doing the prime factorization, which part is looking back, which part is doing the final prediction.
So we're actually getting insights into how these models learn.
Exactly. And maybe the most important takeaway is that the amount of context needed to make these predictions accurately, it scales sublinearly.
Sublinearly, okay.
Which that has really huge implications for efficiency, and it means we might be able to use these techniques for real-world problems, not just in the lab.
Wow, that's a lot to unpack. So let's dive in. First of all, how did they even begin to understand what was happening inside these transformers? It's kind of a black box, right? How did they get those insights you were talking about?
Well, they used some pretty clever techniques to analyze how the model was working on the inside. And what they discovered is that the transformers, they learned to use this mathematical trick by representing the numbers in, we were saying, this residual number system.
Residual number system. I got to be honest, that sounds kind of like something out of Star Trek. Can you break that down for us?
It might sound complicated, but it's really elegant once you get it.
All right, I'm all ears.
So imagine you have a set of prime numbers.
Okay, prime numbers, got it.
The residual number system representation of a number, it's essentially a set of remainders you get when you divide that number by each of those primes.
Okay, I think I'm following so far.
It's like a unique fingerprint for each number based on those leftovers, those remainders.
So instead of listing the prime factors, we're looking at what's left over after we divide by those primes.
Precisely.
Gotcha.
And the remarkable thing is the model learns to do this implicitly. No one tells it to find these prime factorizations.
It figures it out on its own.
Exactly.
So it's not just crunching numbers, it's actually understanding the structure of the LCG and using that to make its predictions.
It's really quite remarkable.
That's incredible. Now, you mentioned that unseen modulus scenario earlier, the one where the model has to figure out the recipe without knowing the ingredients beforehand.
Yeah, that's a tricky one.
How does it even begin to approach that problem?
So in that case, the model actually has to play detective. It has to estimate the modulus first. And the researchers found that a specific attention head within the model, it focuses on the largest number it's seen so far in the context.
Okay.
It uses that as a clue to estimate the modulus.
So it's kind of like saying, all right, the biggest number I've seen so far is this, so the modulus can't be smaller than that.
Exactly. It's using context and a bit of logic to crack the code.
Very clever. So once it has a decent estimate for the modulus, what happens then?
Then it basically does the same thing as in the fixed modulus case. It breaks down the numbers into their residual number system representation using this estimated modulus.
Right.
And then it goes from there.
This is seriously blowing my mind, but it sounds like there's a whole lot more to uncover here, especially with how the model uses context to, like, simplify its predictions.
Oh, absolutely. That's where things get even more fascinating. Okay, so let's get into this whole context thing.
Yeah, how does the model actually use context to make these predictions?
So in that first scenario, the fixed modulus case, right, where the model already knows the secret recipe, the researchers, they uncovered this really clever three-step algorithm that the transformer seems to be using.
A three-step algorithm. Okay, I'm intrigued. What's step one?
First, it figures out the residual number system representation of all the input numbers.
Right, like finding those unique fingerprints based on the remainders after dividing by the prime factors?
Exactly. Step 2 is where the context comes in. The model looks back at a specific number of steps in the input sequence.
It's like checking its notes from earlier.
Kind of, and get this, the look-back distance is directly related to the powers of those prime factors that make up the modulus.
Okay, hold on, let me make sure I'm following. So let's say the modulus is 12, which breaks down into 2 squared times 3.
Right.
Is the model looking back at distances that are powers of 2 and 3?
Exactly. It's like it's learned that those specific distances, they hold some really valuable information.
Interesting.
And by looking back at those points, it can exploit this periodic nature of LCGs. It can basically copy the digits that stay the same over those periods.
So it's not blindly copying, it's like strategically copying the digits that it knows are going to repeat based on the way LCGs cycle.
Exactly. And that takes us to step 3, which is where things get even more intricate. The researchers found that the model uses this look-back information to predict the remaining digits.
So it's kind of like a mix of copying what it knows and predicting the rest based on the patterns it's picked up.
Precisely.
That's really clever. But how did they figure out that this whole 3-step process was actually going on inside the model? I mean, did they like put it under a microscope?
Well, not quite a microscope, but they got pretty granular with their analysis. They pinpointed specific components within the transformers architecture that seemed to be responsible for those different steps.
So they were able to like see which parts of the model were doing the prime factorization, which parts were doing the look back, and which parts were making the final prediction.
In a way, yes. They looked at the attention patterns, the activation of different neurons, and they even tried like pruning certain parts of the model to see how that affected performance.
Fascinating. So they're really piecing together the puzzle of how this thing works.
Yeah, it's like detective work, but for AI.
I love it. Okay, but now let's talk about that other scenario, the one with the unseen modulus, where the model has to figure out the recipe without knowing the ingredients beforehand.
Right, that adds a whole new layer of complexity.
Yeah, because now it's not just following a known pattern, it's got to figure out the pattern itself.
Exactly. So the researchers found that in this case, the model uses like a 2-step strategy. The first step is super clever. It uses one specific attention head to actually estimate the modulus.
Wait, an attention head that can estimate the modulus? That's wild. How does that even work?
So by looking at the attention patterns, they noticed that this specific attention head, it consistently focused on the largest number in the context.
The largest number, okay.
And it uses that as a starting point to guess the modulus.
So it's basically thinking, okay, if the biggest number I've seen so far is this, then the modulus can't be any smaller than that.
Exactly. It's using its knowledge of how LCGs work to make a pretty educated guess.
That's impressive. And then what? Once it has that estimate?
Well, once it has a decent estimate for the modulus, it pretty much goes back to what we saw in the fixed modulus case.
So it does the residual number system breakdown based on that estimated modulus, does the look-back thing, and then makes its predictions.
Yep, that's the gist of it. Of course, because the modulus is estimated, it might not be perfect, so there's a bit of room for error.
But it's still getting good results, even with that added uncertainty.
Oh yeah, the accuracy is still pretty impressive, which really shows how flexible and powerful these transformers are.
Okay, this is all incredibly cool, but I've got to ask, how in the world did they train these models? We're talking about potentially billions of digits and some pretty heavy-duty math. Did their computers just melt?
Haha, that's a great question. And it brings us to another fascinating aspect of this research, like the whole challenge of scaling these models and the surprising efficiency they demonstrated.
Okay, I'm all ears. How did they handle all that data?
Well, they used some clever techniques to make the training process a bit more manageable. One key thing was this thing called base B tokenization.
Base B tokenization. Sounds complicated.
It's actually not that bad. It's basically a way to break those giant numbers into smaller chunks that the model can handle more easily.
So instead of feeding the model a billion-digit number all at once, they're chopping it up into smaller pieces.
Exactly, like cutting a giant pizza into slices.
Makes sense. But what's this base B business all about?
So the B in base B, it refers to the base of the number system they're using for tokenization. Like we humans usually use base 10, right? We have 10 digits, 0 through 9.
Right.
But computers, they use base 2 binary with just zeros and ones.
Oh, so they're converting those massive numbers into binary or maybe some other base and then feeding those smaller chunks to the model.
Exactly. And what's interesting is that the choice of base actually made a difference in how well the model performed. They found that base 256, which lines up nicely with how computers store data in bytes, worked particularly well for moduli that were powers of 2.
So the model isn't just learning about abstract math, it's also picking up on how numbers are actually represented in the digital world.
It's really cool how those things are intertwined and how these models can pick up on those connections to learn more effectively.
This makes me think about how important data representation is in general, not just for transformers, but for all kinds of machine learning.
It's absolutely crucial. Choosing the right way to represent your data can make a huge difference in how well a model can learn and generalize.
Okay, so back to the training process. You mentioned earlier that the amount of context needed for accurate predictions scales sublinearly. What does that actually look like in practice?
So as the researchers scaled up the moduli, they naturally needed to increase the context length, the amount of information they gave to the model.
Right, makes sense.
But the key takeaway is that the amount of context needed didn't increase at the same rate as the size of the moduli.
So it's like the model becomes more efficient as the numbers get bigger. It needs relatively less information to figure out the pattern?
Exactly. They saw this sublinear scaling in both the fixed and unseen modulus scenarios, which is really remarkable.
That's pretty impressive. It suggests that the model is developing a pretty deep understanding of how LCGs work. It's not just memorizing patterns, it's actually understanding the underlying structure.
It definitely points to a really sophisticated level of generalization, which is super exciting.
Speaking of exciting, this research has huge implications beyond just pseudo-random numbers, right? If transformers can crack this code, what other kinds of complex systems could they potentially understand and predict?
That's the million-dollar question. It's a bit mind-blowing to think about. Just imagine applying these techniques to financial markets, where what seems like random fluctuations might actually have hidden patterns.
Or weather forecasting, where understanding those hidden algorithms that drive the atmosphere could lead to way more accurate predictions.
Exactly. Or even things like protein folding and drug discovery. Uncovering the mathematical rules behind those biological processes could completely revolutionize those fields.
It's like opening up a whole new world of possibilities. This research feels like a real turning point, showing us just how much potential transformers have to decode the world around us.
It's humbling to think that we're really just starting to explore what these models are capable of. Yeah, and it's not just about the data size, it's also about how much context the model needs to see to make those predictions accurately.
Right, because as you scale up the moduli, you'd naturally expect to need more and more context to maintain accuracy.
Exactly. The patterns get more complex, you need more information to work with.
But you mentioned sublinear scaling earlier, so what's the catch?
The cool thing is, the amount of context the model needs doesn't actually increase at the same rate as the size of the moduli.
So it's like the model gets more efficient as the numbers get bigger. It needs relatively less information to crack the code.
Precisely. They saw this in both the fixed and unseen modulus cases, which is really remarkable.
That's wild. It suggests the model isn't just memorizing patterns, it's actually learning something fundamental about how these LCGs work.
Yeah, it's like it's developing a deeper understanding of the underlying structure.
Which opens up some pretty mind-blowing possibilities beyond just predicting pseudo-random numbers. If transformers can crack this code, what other complex systems could they be used to understand and predict?
That's the question that keeps me up at night. Imagine applying these techniques to something like financial markets. What if those seemingly random fluctuations actually have hidden patterns that a transformer could pick up on?
Or weather forecasting. Uncovering the hidden algorithms that drive our climate could revolutionize how we predict weather patterns.
Exactly. And think about fields like protein folding or drug discovery. If we could use transformers to understand the mathematical rules behind those biological processes, it could lead to some incredible incredible breakthroughs.
It's like we're just scratching the surface of what these models can do. This research feels like a real turning point.
I completely agree. It's both exciting and a little humbling to realize how much we still don't know about what these models are capable of.
Well, folks, there you have it. We've taken a deep dive into the fascinating world of pseudo-random numbers, residual number systems, and the incredible power of transformers.
We've seen how these models can not only crack codes and exploit mathematical tricks, but also learn from the very way computers represent information.
It's been a wild ride, and this research has definitely left me with a sense of awe and a burning curiosity to see where this field goes next.
I think we're just at the beginning of a very exciting journey. Who knows what other mysteries will unravel with these powerful tools in the years to come.
If you're as intrigued as we are, we highly encourage you to check out the full research paper. There's a whole lot more to explore beyond what we've covered today.
And as always, keep those minds curious and stay tuned for more deep dives into the ever-evolving world of AI research.